Okay, so let's continue our discussion of chapter 7, focusing on alkenes. We talked about degree of unsaturation calculations for carbon, hydrogen, oxygen, and halogens. How do we handle other elements? Well, the most common element that you're going to need to be cognizant of is degree of unsaturation calculation for nitrogen. So nitrogen has 3 bonds, it's trivalent, and in turn, whenever we replace a carbon with a nitrogen, we end up adding 1 more hydrogen to our original hydrocarbon. So in order to fully and correctly calculate the degree of unsaturation, what you're going to do is you're going to ignore the nitrogens and you're going to subtract 1 hydrogen from every nitrogen that you ignored. So for example, looking at this below structure, C5H9N, we're going to ignore 1 nitrogen. So in turn, that means we're going to subtract 1 hydrogen from our total. So rather than treating C5H9N as C5H9, it turns into C5H8 for our degree of unsaturation calculation. So the full formula for degree of unsaturation is we take 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of halogens minus the number of hydrogens over 2. So just like before, let's try to calculate the degree of unsaturation for C4H7N. Okay, so let's take a moment and let's try to use this degree of unsaturation equation, and let's try to calculate the degree of unsaturation for C4H7N. So just as a reminder, when we have C4H7N, we treat this structure as if we had no nitrogens and 1 less hydrogen. So it would turn into C4H6. If we calculate the DU for C4H6, that gives us 2 times the number of carbons, which is 4. Okay. Plus 2 minus the number of hydrogens, which is 6, over 2. So that gives us a degree of unsaturation calculated of 2 for the following molecule. Now, let's try and see if the long form equation matches our proposed degree of unsaturation calculation. So let's take a moment and let's try to calculate the DU using this long form equation, and let's try to share our responses in the chat. So continuing on, does anyone have a proposal for the degree of unsaturation for C4H7N? So looking at the equation for our degree of unsaturation, we have 2 times the number of carbons plus 2 plus the number of nitrogens. We have 0 halogens, so we'll subtract 0, and we have 7 hydrogens. We're then going to divide by 2. So looking at our total in this case, so that in turn gives us a total of 4 over 2, which in turn gives us a calculated degree of unsaturation of 2. So whichever method you find comfortable for handling nitrogen, though it's really important to be able to calculate DU, because when you're performing structural analysis, we'll essentially have to figure out the DU in order to begin to narrow down the number of possible structures that we can have. I see the comments in the chat. We'll talk about that towards the end of lecture, and I'll provide a little bit of explanation and elaboration. But we'll address the current lecture topic for now, and I'll address some of these other questions in the chat towards the end of lecture. Okay, so let's keep going. Let's keep going now. So in terms of naming alkenes, we're going to name, for naming alkenes, they're named very similarly to alkanes, except this time we have to specify the location of our functional group and specify in the name the presence of a functional group. So first, we're going to name the parent hydrocarbon chain by finding the longest carbon chain that contains the carbon-carbon double bond. Okay, so in this case, if we compare these two structures, even though there is a theoretical longest chain that would have 6 carbons, the 6-carbon chain does not contain the alkene. So your parent chain is the longest chain that contains our alkene functional group. So in this case, our longest chain is 5 carbons, so it would be named as pentene. Additionally, because we have an alkene functional group, our carbon numbering must start from one side of the molecule, pass through the double bond, and end at the other side of the molecule. Okay, from this, we're going to count carbons to give the smallest possible locant number for the carbon-carbon double bond. It is considered the highest priority group. And you're going to use the lowest carbon locant number to indicate the double bond location. So for example, if you have a structure like this, we're going to count in a way where we assign the smallest possible locant number to our alkene. So considering our two counting methods, the method that gives us the smallest locant number would be assigning the alkene as it starts at the 2 position. So this would be 2, 1, 2, 3, 4, 5. This would be 2 pentene. If you're being fully accurate, we'd call this 2E pentene. We'll talk about that in a moment. Okay, so the central point, you assign your carbon numbers to give the smallest locant number to the alkene. It's the highest priority functionality. Additionally, substituents must have the lowest possible numbers after assigning the lowest possible locant for the carbon-carbon double bond. So our normal substituent rules still apply after we've dealt with our alkene. So next we're going to number and name the alkyl substituents following the alkyl group nomenclature rules. So you're going to write your substituents in alphabetical order, specifying the carbon number for each substituent. Now, just like if there are multiple side chains of the same carbon length, such as multiple methyl groups, we use the same logic when naming multiple alkenes. So if there are multiple alkenes, we use the prefix diene, triene, and you need to specify the location of each double bond. All very standard fare when it comes to naming compounds. Now, the really important part to keep in mind is because we're dealing with an alkene, we have to change our overall chain suffix from ane to ene. And it's common that you put the locant number followed by the suffix ene. Okay, so taking a look at this, at the following set of molecules. So in the first case, our smallest possible locant number for our alkene would be 2. So we'd name it as hex 2-ene. In this case, if there's only one if there's only one functionality, it can also be named as 2-hexene, but hex-2-ene is more common from the IUPAC method. In the second case, it's really important to keep in mind there are two possible methods of counting: the counting method in red and the counting method in blue. For the counting method in blue, my question to all of you is, why is the counting method in red preferred? What is the key distinguishing factor? Why do we count from left to right rather than right to left? What is our goal with the counting method in red? What's so special about the counting method in red? What rule is helping us here? The alkene is on the same locant, but that's a very good thing to consider. It is on the same locant of 3, but as students are noting as well, the substituent on is on carbon 2 rather than 5. So it's named as 2-methylhexene rather than 5-methylhex-3-ene. Does everyone notice how 2 is preferred over 5? Because 2 is a lower locant number. After we've assigned the lowest locant number to our alkene, we also want to optimize our name so it has the lowest locant number for all of our substituents. Does that make sense? Does that address that key point? Perfect. So let's keep going now and let's try to name the following molecules. I'll start us off with this first molecule. So I'm going to set up my locant numbers. So 1, 2, 3, 4, 5, 6, 7. These two pathways are identical length, so both counting methods will give the same result. 1, 2, 3, 4, 5, 6, 7. Okay, so looking at these methods, which counting method gives us the lowest locant number for our alkene? The counting method in red or the counting method in black? Which method gives us the lowest locant number for our alkene? Red, yep, exactly right. 3 is lower than 4. Yep. Okay, so we see this is a 7-carbon chain, so we'll use the hept base. Okay. Since our alkene is at carbon 3, we name it as hept-3-ene. Okay, so far, so good. So far, so good. Now, my question to all of you is, what in turn are our other substituents? What substituents do we have and what carbon locants are they at? What are each of our substituents and their locant numbers? Let's name them out. So what substituents do we have? We have a methyl at the 6th position. Yep. So we have a 6-methyl group. What else? So we checked off that substituent. What other substituents do we have? What other side chains do we have? 3-ethyl, exactly right. Okay, now that we have our side chains, we sort them alphabetically. So this would be 3-ethyl, 6-methyl, 6-methyl, hept, 3-ene. Okay, perfect. So the only thing new really is that our base changes and we have to really focus our carbon numbering on the highest priority substituent, which in this case is our alkene. Does that process make sense to everyone? Does that make sense to everyone so far? Okay, so let's let's try to work on the following two examples. Let's try to name the following two structures, and let's try to propose our names in the chat. Or you can even write out the annotations that you're using and the locant numbers that you're using to justify your proposed names using the annotate tool. So let's work on this example for about 4 to 5 minutes. And if you have any questions, don't be shy to ask them in the chat or verbally. Additionally, if there is anything that you'd like communicated to the class on this question that I could help share with the class, don't be shy to ask, and I'd be happy to assist. These are typical naming problems that you see that integrate concepts from our earlier naming rules for normal alkane systems. So let's try to work on naming these compounds, and we'll discuss this example in about 4 to 5 minutes. So let's try to get some proposed names for each of these compounds in the chat, and then we'll discuss. Or even some questions as you generate the names, that's more than okay to advance our discussion. Additionally, if you'd like, you can try using the annotate tool to add locant numbers to each of our carbons, and that can help us understand the logic that you're utilizing when naming these compounds, and it could allow us to contribute and advance the discussion from that proposed logic. Does anyone have a question? Does anyone have a proposed name that they're coming up with so far? You can even message it privately, and I'd be happy to share that proposed name in the chat, and we'll discuss this example in about another 2 to 3 minutes. I'd like to see some tentative proposed responses. Or if anyone has further questions, I'd also be willing to address those questions. Okay, so we have a proposed name of 2-methyl butane 1,2 ene. Okay. So that's pretty good start, actually. So let's talk a little bit about this. So the locant numbers that were proposed are the following. The locant number, so but 1,3-ene, perfect. Okay, these locant numbers look reasonable. The alkenes at 1 and 3, and the methyls at 2. So we've optimized it so we have the lowest possible locant numbers. So since we have an alkene at 1, 3, we'd name this as buta 1,3 diene. So remember, when we have two alkenes, we name it with the diene modifier. The 2-methyl group is exactly right. So this would be named as 2-methyl buta 1,3 diene, or you can also call this 2-methyl 1,3 butadiene. Both methods are perfectly acceptable. But it's great to see the locant numbers were correct, the suffix was correct, and the starting side chain was named perfectly correctly. So that's great to see. So both of these names are valid for the following structure. So we count in a way to minimize our locant numbers for our alkenes. So we put them on 1 and 3, and minimize our locant numbers for our substituents, which are on carbon 2. Does this first example make sense? Does this first example make sense? So the key takeaway from this example, as we talked about in the rules, if you have a pair of alkenes, rather than naming it as butene, for example, you name it as butadiene. Does that make sense to everyone? Can I get some feedback in the chat that that concept makes sense to everyone? But the first responses that I saw were great in terms of their locant numbers and setting up and correctly assigning the locant numbers for the side chain and the alkenes. So let's take a look at this next example, and let's try to spend another 1.5 to 2 minutes trying to name the following system. So this is a cyclic molecule, but we know how to name cyclic systems from last time. So let's focus on naming this cyclic molecule and assigning our locant numbers. And if you'd like, you can use the annotate tool to share your proposed annotations for the carbon locant numbers. And remember, we want the smallest locant numbers for our alkene and the smallest locant number for our substituents. So we have a proposed name in the chat of 1-methyl cyclohexene. Where's the alkene at? What carbon locant have you assigned for the alkene? Yep, cyclohex-1-ene. Yep, exactly right. Perfect. And it's great to see that we have some consensus among the class. Yes, 1-methyl cyclohex-1-ene is a perfectly reasonable name for the following structure. We're using the following locant number scheme. Okay, perfect. And that in turn gives us the locant number of 1 for our alkene and 1 for our methyl substituent. Does this example make sense? Does this example make sense? Perfect. So let's keep going now. And let's now try to name as our independent examples the following two molecules. So let's work on naming these two molecules. Again, we have another diene system, as well as another alkene with a slightly tricky numbering convention. Remember, you want the lowest, smallest carbon chain that contains your alkene. So let's try to name the following molecules, and then we'll discuss in about another 3 to 4 minutes. And don't be shy to share your proposed responses in the chat or sharing your proposed locant numbers using the annotate tool. So we have a proposed name in the chat of 2-ethyl. So we have a proposed name in the chat of 2-ethyl pentane 1-ene. So when you're naming an alkene, you can just get rid of the ane suffix and just name it as 2-ethyl pent 1-ene. Where because it's an alkene, it now has the ene suffix. So that's one proposed name that we have. The other proposed name that we have is 2-isopropyl bute 1-ene. So to talk about each of these proposed names, let's look at our numbering conventions. So one numbering convention is as follows. The second numbering convention is indicated in blue. Oh, so 2-propyl, okay. Okay, so looking at these two numbering conventions, which of these carbon chains is the longest? Which of these carbon chains that has our alkene is the longest? Which chain has the most carbons? The chain in red, right? So then, should we name our main chain as a butyl chain or a propyl chain? Oh, sorry, a butyl, propyl, or pentyl? How many carbons are in the longest chain? How many carbons are in this red carbon chain? It's 5 carbons, so this would be a pentyl chain. Okay, so following the numbering conventions in red, we notice our alkene is at the 1 position, and we have an ethyl group at the 2 position. So this would be named as 2-ethyl pent 1-ene. Does that make sense to everyone? So we want the longest carbon chain that contains our alkene. Perfect. So let's continue on and let's try to apply what we've learned to the next set of examples. So let's start with the first example from the top down, but you're welcome to propose names for any of the structures in this list. These are typical structures that you'd see both in this chapter, as they're pretty useful substrates, and they're typical examples of naming alkenes. So we have a proposed name in the chat for this first compound of cyclohex, 1,4-ene. And does anyone have a piece of feedback? We have another proposed name in the chat of cyclohex, 1,4-diene. Yep. So when you have two alkenes, you use the di modifier. So instead of ene, it would be diene. So cyclohex 1,4-diene is a perfectly reasonable name for the following compound. Let's showcase the numbering convention that got us here. So we have our alkene at carbon 1 and 4. Remember, you have to count clockwise or counterclockwise around the ring. So this is the smallest possible set of numbers. You can also call this 1,4-cyclohexadiene. That's also a valid name from IUPAC, but this name in the box is more stringently follows the IUPAC naming rules. Perfect, perfect. Let's try to work on these next two examples, and don't be shy to share your comments in the chat, share your locant numbers using the annotate tool, and as I read through the chat, I'll try to convey the student responses. So we have one response of 2,4-dimethyl hex 2-ene. Okay. Let's try to get a few more responses in the chat, a few more comments. Do you agree? Do you disagree? Is there another name that you have proposed? Do the locant numbers seem reasonable? And let's try to get a few more students responding just so that way I can see that there's consensus. Or if you disagree, don't be shy to type that in the chat as well. Okay, so looking at our locant numbers, so we have a methyl group at 2 and 4. So we have 2,4-dimethyl as our substituents. And then it's a 6-carbon chain, so it would be hex. And our alkene's at the 2 position, so we name it as hex 2-ene. So the name for this second structure looks perfect. And just as a reminder, you can enter any of the structures that you see into Marvin Sketch, and it will provide you the name for the structure. So it's a great way of just drawing out structures, trying to name them, and then allowing you to check your work. Okay, so let's look at this last example. And this one you have to be a little bit careful with, the numbering convention. So we have a student proposing a name of 1,5-dimethyl cyclopent 1-ene. Cyclo because it's a cyclic system. That would entail the following counting method. We also have, as an alternative name proposed in the chat, 1,2-dimethyl cyclopent 2-ene, okay? And we also have as another proposed name, 2,3-dimethyl cyclopent 1-ene. Okay, so there are a few options here. Now thinking about our naming rule priority, what gets the first priority in naming? What do we want to give the lowest locant number? What would give the alkene, right? Okay, so if we want to give the alkene the lowest locant number, only these first two options meet that requirement, right? Now, when we think about naming, compounds, do we want the lowest average locant number, or do we want the lowest locant number from start to finish? So which locant number is lower, 1 or 2? Which locant number is smaller? 1, right? So as a result, the numbering method initially proposed was exactly correct, and this compound will be named as 1,4-dimethyl cyclopent 1-ene. So remember, you want the lowest locant number for your alkene, which is 1, and then you want the lowest locant number, not on average, but for each substituent from the first substituent to the last. So you look at each locant number individually, and whichever naming convention gives you the lowest locant number, that method is preferred. Does that method make sense to everyone? Does that make sense? Perfect. It's great to see that students have proposed and provided names for each of these compounds. Let's now talk about naming haloalkenes. So you're going to want to choose the longest chain containing the alkyl halide and the alkene. Okay? Double or triple bonds take precedence over a halogen or alkyl group. So the double and triple bond is the king here. You're going to count carbons so your substituents have the smallest possible locant numbers. In the event of a tie, you're going to assign the smallest locant numbers based on alphabetical order. So you're going to name each halogen and alkyl group alphabetically, specifying the locant number for each. Okay? If you have 2 or more halogens, you're going to indicate the position of each and use the di, tri, etc. prefixes. And the key important feature for halogens is that halogens are lower priority, or are lower priority / equal priority to alkyl chains. So treat a halogen just like another alkyl chain. They only end up with priority in many cases due to alphabetical naming rules. So for example, in this case, even though we have a bromine, we don't have to really accommodate that bromine. We can name in a way that gives the lowest locant number to each of our substituents and to our alkyl chain. That's why it's named as 5-bromo-2,4,4-trimethylheptane rather than 3-bromo-4,4,6-trimethylheptane. The halogens are lower or equal priority to an alkyl chain. Does everyone see that distinction? So it's not like an alkene. You don't have to go out of your way to give the lowest number to the halogen. It's just another substituent. Does that make sense? But I just want to put a star next to this, but remember the alphabetical rules. Just make sure you keep in mind that you remember the alphabetical rules. So if there's a tie, alphabetical order comes into play. So in this case, we have 2 potential numbering conventions. The numbering convention in black or the numbering convention in red. So looking at our 2 proposed names, we can either name it as 1-chloro-3-methyl cyclohexane or 1-methyl 3-chlorocyclohexane. Now, if there's a tie in locant numbers, what is our tiebreaker? What breaks the tie? If there's a tie in locant numbers, what goes first? What gets the lowest number? Alphabetical order, exactly right. So if we have to pick and we compare methyl and chloro, which has C, is first alphabetically, so we give the chlorine substituent the lowest priority number. Does that make sense to everyone? So just remember, in the event of a tie, alphabetical order wins out if you're comparing an alkyl chain to a halide substituent. Does that idea make sense to everyone? Perfect. Okay, so let's try to name the following compounds. So this time we have compounds containing alkenes and halogens, remembering that the alkene takes priority. So I'll do the first set and you'll do the second set. So in this first compound, I'm trying to assign the lowest locant number to all of my substituents. So we see the lowest locant number I can assign to the chlorine would be 2. So this would be 2-chloro-bute-2-ene. Now, this compound's a little bit special in that the alkene has stereochemistry. For those who just sort of have this remembered from our earlier discussion of alkene stereochemistry, what kind of alkene is this? Is it a Z or E alkene? Is it Z or E? We'll talk more about this later, but I want to make sure that if someone is familiar with it, or if someone would like to propose that, this is an important little asterisk that you need to put when naming that we'll expand upon momentarily. So as we see, both of our highest priority substituents are on the same side, so we'd call this a Z alkene. So the full name for this would be 2Z2-chloro-bute-2-ene, where we're noting that this alkene has our bulkiest substituent, our highest priority substituent, on the same side. So 2-chloro-bute-2-ene is the generic name, not accounting for stereochemistry. We'll learn later on, and we'll tie together the concept of alkene stereochemistry with our naming rules to provide names that account for the stereochemistry. But the names that I've seen proposed in the chat looked great. I just wanted to add this additional layer that we're going to consider and that we're going to expand upon later on in this chapter. Does this naming convention make sense? Does everyone see where we're getting these names for this haloalkene species? Does this make sense to everyone so far? The 2Z is indicating that this alkene is a Z alkene. Yeah. So 2-chlorobutene describes this general structure without accounting for stereochemistry, while the 2Z tells us the alkene at the 2 position is a Z alkene. Does that make sense? Perfect. Okay, so let's keep going and let's try to name the following 2 compounds, and then we'll discuss momentarily. Let's try to get some proposed names for these 2 haloalkene compounds, and we'll discuss. So we see a name proposed for this second compound as 2E. Three bromo pent 2ene. Oh, 4 bromo. There we go. Okay. So what does everyone think of this name? Does anyone have another name that they'd like to propose for this haloalkene? The following numbering convention was used in this case. Does anyone have any input, any suggestions, any modifications to this name or structure or numbering convention? So we have in the chat someone suggesting it should be hexene as it has 6 carbons. I would agree with that revision. Yep. So it would be hex 2ene. Yep. Okay. Does anyone else have another proposal? Does everyone have another name? Does this name seem reasonable to everyone? Did everyone have another way of numbering our locant numbers? Do we agree with this proposed name? Do we have a different name that we'd like to share? Just want to see a few more responses in the chat to make sure everyone is comfortable with this. Okay, perfect, perfect. So let's look at the next example. Let's look at this next example. And let's try to name the following cyclic alkene. Remembering that you can only count clockwise or counterclockwise, and you number in a way to give the lowest locant number to the alkene. So we have in the chat a proposed name of 3-bromo cyclohex 1-ene. So what does everyone think of this name? Do you agree? Do you disagree? Is there another name or numbering convention that you think would be more appropriate? So you want to give alkene the lowest possible locant number. So we typically start counting at the alkene because we want to assign it the lowest locant number. Does anyone have another proposed name? Or do we have agreement with this proposed name do we have agreement with this proposed name? Is everyone comfortable with this example? Perfect. So let's keep going and let's really make sure that we're comfortable with this. And let's try to name the following structures. So we had an example to tackle some problems, revise our logic that we use to engage with these problems. And now let's try to demonstrate our mastery of the content by tackling the following examples. So let's try to name the following pair of compounds, and we'll discuss in about 3 to 4 minutes, but don't be shy to share your name proposed in the chat, and I'd be happy to write it on the class whiteboard so that way we can engage and talk about each of these compounds and their names. So for the first compound, we already have a proposed name of 5-chloro, 3-methyl, hex, 1-ene. Okay. You can comment whether you agree or disagree with the name or propose your own name for each of these compounds. Let's try to get a pool of responses in the chat for these two examples, and then we'll discuss. So just to highlight the numbering method used by the student to reach this name, we're using the following numbering method, which prioritizes placing the lowest locant number at the alkene following convention. And for the second compound, we have a proposed name of 3-chloro, 4-ethyl, pent 1-ene. And that's utilizing the following numbering convention. And we have a student proposing that rather than pent, it should be cyclopentene, which makes sense to me as it's a cyclic species. So it's cyclopent 1-ene. Perfect. So do we have agreement with these names? Does anyone have another name that they'd like to propose for these structures? And we'll talk about these examples and sort of summarize the logic behind these examples in about another minute. If you have another proposed name that you'd like us to discuss, don't be shy to propose your alternative name for these compounds in the chat. So in terms of numbering, if you can count in a way that gives chlorine a lower locant number, that counting method would be preferred. So for example, the counting method in black would be preferred over this counting method because it gives the lowest locant number of 3 to the chlorine substituent. So to summarize the logic behind this, so we prioritize our alkene. So our alkene has locant number 1. It's a 6-carbon chain, so it would be hex 1-ene. We have our methyl at the 3 position. And what's great to see is that you're even alphabetizing them already. So that's great to see. So we have 3-methyl hex 1-ene. And what about our chlorine substituent? What carbon is our chlorine substituent at? It's on carbon 5, so we name it as 5-chloro 3-methyl-hex-1-ene. So the student proposed name is exactly correct. Now let's look at this next example. So as we discussed, we have two numbering conventions. We want the lowest locant number for our alkene. So we have either the counting method in black or red. Those are the only two we can viably come up with that give a locant number of 1 for our alkene. If we had a choice, we want the lowest locant number for our substituents, and the counting method in black gives us a locant number of 3 for our chlorine, which is preferred. So this would be 3-chloro-4-ethyl cyclopent-1-ene. So the student proposed name that we obtained via class collaboration was perfectly reasonable. Do these responses make sense to everyone so far? Does this make sense to everyone so far? Keep in mind on the ACS and other exams, you may be asked to draw structures that are used in reactions from the name. So you need to be familiar with the IUPAC name. Let's look at this last compound, just so that way we have a little bit of diversity in terms of the naming. And let's try to name the following compound. So this will be one of our last naming examples before we move on to the next section of this chapter. Yep, exactly right. So let's try to get some proposed full annotated IUPAC names in the chat, and then we'll discuss. So we have a proposed name in the chat of 3-iodo 2,5-dimethyl 4-ethyl. One moment. Sorry about that. 3-iodo 2,5-dimethyl 4-ethyl hept-2-ene. And so the question is, we're not sure if we count the di prefix in alphabetical order. So what does the class think? What does the class think on that? Is the di prefix counted? Does anyone have an alternative name? Do we agree with the proposed name? So, remembering our rules from the previous chapter, the di, tri, etc. prefixes are ignored. So if we compare methyl to ethyl, ethyl should be first alphabetically. So this would be 3-iodo 4-ethyl. Oh, right. And the student even noticed that based on the alphabetical order, ethyl should be first. Great to see. So we have 4-ethyl, 3-iodo, 2,5-dimethyl, hept-2-ene. Perfect. So now everything's in alphabetical order, E before I, and then E and I go before M. So 4-ethyl, 3-iodo, 2,5-dimethyl. What does everyone think of this name? Do you agree with this name? Do you disagree with this name? So just to highlight, these are the locant numbers that are used. And this name that we obtained after sorting things alphabetically looks exactly correct. So it's great to see that the class can collaborate and reach a reasonable solution for the final name of this compound. Any questions on IUPAC naming rules and naming compounds? Okay, so let's keep going now, and let's talk a little bit about alkene stereochemistry and just review. This will be really important because you need to be able to understand and identify the stereochemistry of our alkene, because many of the reactions that we'll cover in this next chapter are stereospecific. If you start with a certain alkene geometry, you will get out a product with a defined stereochemistry based on your starting material. Okay, so as we know, our pi bond prevents rotation. So there's a very large barrier to rotation for our pi bond. So functionally, we're not going to, the pi bond can be considered functionally non-rotatable. Okay. There are two main types of alkenes. We're used to the old school method where we name our alkenes as cis and trans. Cis when our substituents are on the same side of the alkene, trans when the substituents are on opposite sides. Okay. Now, where this cis and trans naming convention falls apart is when you start to deal with alkenes with multiple substituents. When you say cis or trans, it's ambiguous to what substituents you're referring to. So, as we've learned previously, we utilize the IUPAC convention of Z and E alkene assignments. So as a review, we rank each group on each side of the alkene separately in order of priority. Remember, priority is based on atomic mass. The larger the atomic mass, the higher the priority. If the highest priority groups are on the same side of the alkene has a Z configuration. If the highest priority groups are on the opposite side of the alkene, it has the E configuration. And Z and E are derived from the fact that these are sort of derived from German, where Z refers to substituents or objects close together on the same side, while E refers to substituents or objects on the opposite side. Okay, so for example, we have two alkenes. This alkene, as we see, our fluorine and oxygen are our highest priority. They're on the same side, so we call this a Z alkene. We're not going to try to name this quite yet because we haven't covered how to name ethers yet. But I just want you to note substituents on the same side, Z alkene. In the second case, we have our high priority substituents on the opposite side of our alkene, so we call this an E alkene. Does that make sense? Okay, so let's keep going now. So in cases where there are multiple substituents and when we're utilizing the IUPAC convention, just to delve into this ranking system, you rank each group on each side of the alkene separately in order of priority, where atomic number dictates which groups are higher priority. So for example, a chlorine is higher priority than a methyl group. And likewise, a methyl group, which has a carbon, is higher priority than a hydrogen. Now, one thing you really have to keep in mind is that if the atomic numbers are the same, you compare at the next connection point at the same distance, and you compare until something has a higher atomic number. Just as a refresher on that, multiple bonded atoms are equivalent to the same number of single bonded atoms, and the substituent is often best drawn with the connections shown and no double and triple bonds. So we can convert our carbonyl into 2 carbon-oxygen single bonds. And that makes it easier to count and rank groups based on priority. And again, I have to emphasize, it's not total priority. It is for each atom individually. As you count your substituents going farther and farther away from our central carbons, which substituent is the higher priority at each stage. Okay, so let's take a look and let's try to assign the following alkenes as E or Z. So I'll do this first example and you'll do the second. So bromine compared to fluorine, bromine is higher priority, it has a higher atomic mass. Chlorine is obviously higher priority than hydrogen. So looking, I'm going to circle my high priority substituents. They're on the same side, so this would be a Z alkene. If you're curious how this would be named, you'd call this Z 1-bromo, 2-chloro, 1-fluoroethene. And I guess it would be 1Z, but we just replace that with Z. So this would be a Z alkene. Does this first name make sense? Does this first proposed name make sense? Okay. So let's try to work on, and let's just make sure we're comfortable, and let's try to assign these 2 alkenes, 1 and 2, as Z or E, just to make sure that we're comfortable with the most basic form of E and Z assignment. So does anyone have any proposals in the chat? What's the assignment? So we have the left assigned as Z because our high priority substituents are on the same side, while the right, it's assigned as an E alkene because our high priority substituents are on opposite sides. Yep, exactly right. Okay, so now that we've done some simple examples together, let's showcase, and I'll showcase this example of a more complicated structure. Okay, so first and foremost, tracing out 1 carbon away, we have an oxygen attached. Okay, that's immediately higher priority. So oxygen, carbon and 2 hydrogens beats out 3 carbons and a hydrogen because oxygen is higher priority. On the right, we have 2 carbons and 2 hydrogens. Whoops, sorry. One moment. So we have a carbon and 3 hydrogens versus 2 carbons and 2 hydrogens. Carbon beats out hydrogen, so this ethyl group is priority 1. They're on opposite sides, so this would be an E alkene. Does that logic make sense to everyone? Does everyone notice how it's not the total priority of your substituents, but any tiebreaker between your substituents? The highest priority atoms leads to the highest priority group. So oxygen beats out carbon. And as a result, even though we have more carbons, the substituent with the oxygen is still higher priority. Does that make sense? Perfect, perfect. So let's try to apply what we've learned on the following examples. So these are really designed to make sure you understand the priority rules in detail. So let's try to work on these examples and we'll discuss in about 4 minutes. And these 2 examples will be the last ones that we cover in this session. But don't be shy to provide your proposed assignments in the chat. And if you have any questions as you go through and try to assign priority, don't be shy to ask, and I'd be happy to provide feedback. And remember, count 1 atom step at a time. That's a key hint for that first example. And don't be shy to share your proposed responses in the chat, and we'll discuss in about 2 to 3 minutes. We're not trying to name these compounds, we're just looking at whether the alkene is E or Z. So we have a tentative assignment for the first alkene as E, okay? So let's talk about this first example. So counting, we're going to count our substituents 1 species at a time. So we have carbon versus oxygen. What is higher priority, carbon or oxygen? Oxygen, yep. So this will be priority 1. Okay, counting 1 carbon away on the right. We have 3 carbons and a hydrogen versus 2 carbons and 2 hydrogens. So which group is higher priority? The top or the bottom? The top. So looking at this, I see I have both my high priority groups on the same side. So it would be a Z alkene. Does that make sense? Does that process make sense? Perfect. So let's try to apply what we've learned in that previous example to this second example. So let's work on this second example for a little bit, and then we'll discuss. Well, let's try to get some stereochemistry assignments for the second alkene using this first example as a representative guide. And we'll discuss momentarily. So we have some proposals that this alkene is E. What does the rest of the class think? Do you agree? Do you disagree? So we have some students proposing E, others proposing Z. So let's talk about this. So first, let's count one carbon out. Okay, so attached to this, so let's draw out this nitrile as how it should be visualized. So a nitrile can be thought of as like this, right? Where each of our double and triple bonds can be treated as a series of single bonds. And now we'll draw out our double bonds in the exact same way. Okay, so now my question to you is if we go one carbon out, so we have a carbon attached to 3 nitrogens and a carbon versus an oxygen, a carbon, and 2 hydrogens. What wins out? What has the higher atomic mass? Oxygen or nitrogen? What has the larger atomic mass? Oxygen, right? So this bottom group would be priority 1. On the right-hand side, we count one carbon out. We have a carbon attached to 4 carbons versus a carbon attached to 3 carbons and a hydrogen. Which group is higher priority? The bottom group with 4 carbons, yep. And it's not because it's just 4 carbons, but because carbon is higher priority than hydrogen. So now these groups are on the same side. The high priority groups are on the same side of our alkene. So would that be Z or E? Z. Yep. Exactly right. So this has been really productive so far. It's great to see students working through these examples. So we're now a little bit more comfortable naming compounds, assigning the stereochemistry. We'll do more practice next session. And from there, we'll start to introduce stereochemical labels into our naming conventions. So this is a good point for us to pause